tutorial is going to consider the UV fluorescent microscope. And notice that the UV fluorescent microscope is an improvement on the basic design of the primitive UV microscope that we discussed about in previous tutorial. And notice that by that inherent design of the UV microscope, as we discussed, we came to realize that UV microscope would have to use quartz lenses throughout, because UV light is unable to penetrate through the normal glass lenses. And quartz lenses being pretty much expensive was a huge obstacle in the utilization of these UV lights in microscope in general. We also got to notice that we had to use a photographic screen or a fluorescent screen, owing to the fact that the image that is formed by the UV light is not visible to the human eye, and also owing to the fact that UV light is carcinogenic and can induce mutations resulting in cancer and all of those things. Then we would have to exercise a lot of caution. And all of these undesirable effects are to some extent being addressed in the later design of that model of the UV microscope into what we call the UV fluorescent microscope. So how is this done? This is done by exploiting another principle called fluorescence. And the principle of fluorescence, even though it has a lot of physics and chemistry in it, is a principle that would be able to allow us to convert light of shorter wavelengths into light of longer wavelengths. And if you remember the previous equation that I gave you, you realize that if you have the equation E equals hc over lambda, that is energy of light is equal to the Planck's constant times the speed of light in vacuum all over the wavelength of that light. You always have to come to the understanding that the shorter the wavelength, the higher the energy of that particular light. And so light of shorter wavelengths have higher energy, and light of longer wavelengths have some smaller energy in that particular regard. It is these same principles that in basic chemistry allows transition elements, for example, to form colored compounds. So for example, transition elements, they have a dd transition in their d orbitals because they have upper d orbitals and lower d orbitals. Electrons in the lower d orbitals gain energy, they get excited and move to the upper d orbitals. They lose energy by a number of conditions and then they decelerate. When they are decelerating, the amount of energy is lower than the initial energy that got them excited. And so that reduction in energy will correspond to an increased wavelength, because you know that whenever light has a higher energy, it has a shorter wavelength, and when it has a lower energy, it has a longer wavelength. And so what happens in transition metals, for example, is that when they decelerate by losing energy, that particular loss of energy will give them an amount of energy that corresponds to a longer wavelength than the initial wavelength that they had. And that particular wavelength of light that they now have will correspond to a certain color in the electromagnetic spectrum. And that's in the visible spectrum of light. And that particular wavelength corresponding to a given color will give them the color of that particular element in aqueous solution. So for example, that's why copper is blue, that's why ion 2 is green, that's why ion 3 is yellow in that particular regard. Now let's look at this principle as applied to biological systems in all of these instances. So it's important to note that biological systems or biological specimens have atoms of lower energy, atoms of low atomic numbers particularly. Now, just trying to portray the principle of fluorescence quite briefly, not going into the details, what you get to realize is that these specimens absorb light. And so initially, the specimen, UV light passes through the specimen and the specimen absorbs the light. Some of the light is reflected as heat, some of the light is used to knock off electrons from the specimen, and generally work is done by that particular light ray that enters the specimen. And all of these will cause the light rays that emerge from the specimen to have a lower energy than the initial light ray that entered. And that reduction in energy of light, is going to correspond to a longer wavelength of that light than we had earlier. And that longer wavelength of light in the context of fluorescence is long enough to create a shift from the UV spectrum of the electromagnetic wave to the visible spectrum. And so in that particular regard, we use UV light through the specimen, and through the principle of fluorescence, we exploit and enhance that principle of fluorescence such that the UV light is converted to light of lower energy. And that's because the UV light loses energy. And when it loses energy, it now has a longer wavelength, such that now that longer wavelength cannot be within the UV spectrum again, such that it shifts to the visible spectrum. And the visible spectrum that has a longer wavelength does not have all the harms that are associated with the UV light. And so now this new light that comes from the specimen can be able to pass through our glass lenses. It is visible to our eyes and it's not carcinogenic. And so this is how the principle of fluorescence is exploited to enhance and eliminate all the harms that are associated with the UV microscope in that particular regard. And so you realize that in a UV fluorescent microscope, unlike the UV microscope where all the lenses have to be made of quartz lens, in a UV fluorescent microscope, it is only the condenser lens that is made up of quartz lens. Then the light passes through the condenser lens, gets to the specimen. And once it gets out of the specimen, it's in a visible spectrum because it's been converted to light of longer wavelengths. And so now the objective lens can be made up of normal glass lens. The eyepiece lens is also made up of normal glass lens. So in a UV fluorescent light microscope, it's only the condenser lens that is made up of quartz lens, and any other lens is going to be, ladies and gentlemen, made up of normal glass lens.